A computer processor, at its core, is completely isolated. It sits in the dark, sealed off from the physical world, blind, deaf, and entirely numb to everything happening around it. The physical world operates in analog states. It is a constantly shifting environment of rising temperatures, shifting atmospheric pressure, and chemical concentrations. But the machine only understands a single language: electricity. To bridge that gap, we rely on the sensor. A sensor is a physical body or detector that reacts to a specific environmental condition, like a piece of metal expanding under heat, or a thin film bending under pressure. But a physical reaction alone isn't enough. That change has to be translated. This is the job of the transducer, a component that takes that physical energy and converts it directly into a readable electrical signal. Without this precise translation from a physical action into an electrical voltage, the entire digital computing revolution would be trapped inside a silicone box, totally unable to interact with the reality outside. To see how this translation works in practice, let's look at a macro-level example, measuring physical displacement. This diagram shows a rotary potentiometer. As an object pulls the extended cable, it rotates the threaded drum, which moves an internal wiper across a resistive strip. This mechanical movement directly converts the linear pull into a changing electrical resistance. We can take this principle and scale it down from a macroscopic device to the microscopic level. This brings us to microelectromechanical systems, or MEMS. This cross-section shows a MEMS pressure sensor. Notice the silicone die with diaphragm suspended over the evacuated cavity. External pressure forces this diaphragm to bend inward. This distortion changes the silicon's electrical resistance, creating a readable voltage signal. All sensors operate on this exact premise. Whether tracking the pull of a steel wire or weighing the microscopic pressure of the atmosphere, they convert physical distortion into a digital voltage. In a global network where data must be routed instantly, a raw voltage signal lacks context. It contains background electrical noise and isn't yet formatted into a data packet that a remote computer can actually read. This diagram shows a more integrated architecture, the smart sensor. By directly coupling the raw physical base sensor with a local microprocessor, the device processes its own input. It filters out erroneous noise and formats raw readings into clean data locally. Once the data is structured, integrated Internet of Things, or IoT, communication capabilities assign the reading a unique identifier. This allows the localized data to be transmitted globally in real time. These devices function as autonomous nodes. They filter their own inputs and participate in a sprawling communication web that spans the entire planet. When we scale these networked nodes up to the global level, we can deploy them into the wild to monitor complex, dynamic ecosystems like regional air and water quality. An air pollution sensor works by pulling in ambient air and using electrochemical reactions or laser scattering to identify specific toxic gases and particulate matter. Decades ago, this level of chemical analysis required the heavy, specialized equipment seen here. Today, those large analyzers have been replaced by miniaturized smart sensors. They are embedded quietly into urban infrastructure, providing continuous, invisible, real-time data feeds directly to city planners. The primary strength of these modern networks is reach. We can safely deploy highly sensitive, low-power data collection units into austere, remote, or dangerous natural environments, where they act as persistent early warning systems. But this reach introduces real vulnerabilities. Placing units in remote locations creates high logistical costs when physical recalibration or maintenance is required. Furthermore, every networked node is a potential entry point for cyber tampering by malicious actors. Despite the maintenance and security risks, this web of thousands of sensors forms an indispensable digital nervous system. It provides humanity with the real-time feedback loop required to understand and ultimately protect the Earth.